Hi everyone, and welcome to this audiobook designed for the EWRB Electrician Regulation Exam. My name is Aria, and I work alongside Whitroy as an electrical tutor. This audiobook explains the exam topics in simple spoken language, making it easier to understand and review anywhere, anytime. Before we get into the lesson, I want to explain what this audiobook actually is. This audiobook is not a word-for-word reading of ASNZS 3000. You must always refer to the real standard when you're doing electrical work or preparing for an assessment. What we do here is take the important ideas from the standard and rewrite them in simple spoken English. The goal is to make the rules easier to understand, easier to remember, and easier to revise, especially when you're listening on the go. So think of this audiobook as a learning guide, not a replacement for the actual standard. Alright, let's begin. Today we're beginning section 2 of ASNZS 3000. In this section we'll look at how to choose electrical equipment and how to install it so the whole system stays safe, reliable, and easy to work on. We'll talk about how circuits are arranged, how protective devices need to work together, and why isolation and switching are so important. We'll also look at RCDs, overvoltage and undervoltage protection, and the requirements for switchboards, including where they can be installed and how they must be built. Section 2 is all about making good decisions that support safety and performance in real installations. So let's get started and walk through the clauses one by one in simple spoken language. Clause 2.1.1 Application. This clause tells us that Section 2 sets the basic rules for selecting and installing all switchgear and control gear. To meet the safety requirements in Part 1, everything must follow the guidance in this section. So it sets the foundation for how we choose and use equipment throughout the entire installation. Clause 2.1.2 Selection and Installation. This clause explains what switchgear and control gear must be able to do. They must allow safe control and safe isolation of circuits so we can test, repair, or maintain equipment. They must automatically disconnect the supply during faults such as overloads, short circuits, or earth leakage problems. They must also protect equipment from unsafe voltage levels. And they must be installed in suitable locations where they are protected from damage and are easy to reach. The key idea is that equipment must not only work but must help maintain safety at all times. Clause 2.2 Arrangement of electrical installation. Clause 2.2.1 Circuits. Clause 2.2.1.1 General. This clause tells us that an installation must be divided into circuits in a sensible way. We think about how equipment operates, how much current it draws, and what needs to stay reliable. Circuits should be arranged so a fault on one part does not shut down large areas unnecessarily. Lighting, power, heating, motors, and safety services should each be placed on circuits that make sense for their function. Safety service circuits must always be kept separate from normal circuits so they stay active during emergencies. Clause 2.2.1.2 Common Neutral. This clause explains when a neutral conductor may be shared between circuits. A neutral can be shared only when it is safe to do so, and when the continuity of the neutral does not depend on terminals of equipment like switches. When circuits share a neutral, the active conductors must be switched or protected together so the neutral is never left carrying current alone. The shared neutral must be clearly identified at the switchboard so anyone working on it understands the arrangement. The main idea is that shared neutrals are allowed, but only when installed safely and clearly marked. Clause 2.2.2 Maximum Demand. Maximum demand is the highest likely load on the installation. We calculate or assess it so we can size mains, submains, and final circuits correctly. It can be found by calculation, by assessment, by measurement, or by using protective device settings. If actual measured demand turns out to be higher than the calculated value, then the measured value becomes the correct maximum demand. This ensures cables, switchboards, and protective devices can safely handle the load. Clause 2.2.3 Selection and Installation of Conductors. This short clause simply says that all conductors must be chosen and installed according to Section 3, which covers conductor sizing and installation methods. So this clause acts as a pointer to the detailed rules found later in the standard. Clause 2.2.4 Operating characteristics of equipment. Clause 2.2.4.1 General. Equipment must suit the way it will be used. If a device performs more than one function, it must meet the safety requirements for each function. Clause 2.2.4.2 Voltage. Equipment must have a voltage rating that matches the system voltage. Clause 2.2.4.3 Current. Equipment must carry the normal load current and withstand abnormal currents long enough for the protective device to operate. We think about inductive loads, heating loads, and any special characteristics. Clause 2.2.4.4 Frequency. If the frequency of the supply affects how a device works, then the device must be rated for the system frequency, which in New Zealand is 50 Hz. Clause 2.2.4.5 Power. Equipment must handle the maximum power it will be expected to deliver without overheating or becoming unsafe. Clause 2.2.4.6 Effects on operator or other equipment. When equipment is used normally, it must not create danger. It must not shock, burn, or interfere with other equipment. Switching operations must not cause unsafe conditions for the operator. Clause 2.3 Control of electrical installation. Clause 2.3.1 General. The installation must have devices that allow safe switching, safe operation, and safe maintenance. These devices include isolation switches, emergency shutdown switches, mechanical maintenance switches, and functional switches for normal control. If one device performs more than one of these jobs, it must meet the rules for each function. Clause 2.3.2 Common requirements. Clause 2.3.2.1 General. Every circuit must be able to be isolated from the supply. Isolation must require a deliberate action so it cannot happen by accident. We use things like padlocks, warning tags, or locked enclosures to prevent accidental operation. When equipment is supplied by more than one source, we must clearly warn people working on it so they know all sources need to be isolated. And if stored electrical energy exists, such as in capacitors, we must provide a way to safely discharge that energy. Clause 2.3.2.1.1 Alternating current systems. In AC systems, all active conductors must be isolatable. A neutral may only be switched in special situations, and when it is switched, it must open and close together with the active conductors. The neutral must never be left floating, as this can create dangerous voltage levels. Some circuits, such as fire pump controls, have special rules, but the general idea is simple: actives must be able to be isolated, and neutral switching must be safe and properly linked. Clause 2.3.2.1.2 Direct current systems. In DC systems, each pole must also be able to be isolated. There are a few exceptions, such as when one conductor is permanently connected to Earth, but the overall rule is that DC circuits must have safe, clear isolation. Clause 2.3.2.2 Devices for isolation. Clause 2.3.2.2.1 General. A device used for isolation must disconnect all active conductors. It must clearly show when it is open or closed, and it must not fall or snap into the closed position by accident. It must withstand the electrical stresses expected in the installation. If the isolator cannot break load current, we must use interlocking, warnings, or other controls so it is never operated under load. The key idea is safe, reliable, deliberate isolation. Clause 2.3.2.2.2 Identification. Every isolator must be clearly identified. Anyone working on the installation must immediately know what the device isolates. Labels or symbols may be used as long as they are clear and permanent. Clause 2.3.3 Main switches. This clause explains why we need main switches. A main switch allows a person to shut off power quickly and safely, including emergency services if they arrive during a fire or accident. It also helps keep important safety services running when other parts of the installation are isolated. The key idea is that the main switch is the primary control point for the whole installation. Clause 2.3.3.1 General. This clause tells us that every electrical installation must have a main switch located on the main switchboard. If the installation has more than one supply, such as a generator or solar system, each supply must have its own main switch. The main switch must be placed where it can control the whole installation or the part it is meant to protect. Alternative supplies may sometimes be connected in different locations, but only when allowed by other standards. Clause 2.3.3.2 Number of main switches. This clause explains that we should only install the number of main switches that are needed for safe and effective operation. In a normal home, you usually need only one main switch for the whole installation. If a building has separate metering for different parts, or different tenants, each part must have its own main switch so it can be isolated without affecting others. The aim is to keep things simple but still provide safe control where it is needed. Clause 2.3.3.3 Location. This clause is about where we place main switches. Main switches must be easy to reach, and the switching handle must not be higher than about 2 meters so most people can operate it safely. Main switches must not be located in places where someone could operate them accidentally or where access is restricted for safety reasons, such as public land or special equipment spaces. If an installation has more than one occupier, each occupier must have access to a switch that isolates only their part of the installation. Clause 2.3.3.4 Identification. This clause explains that every main switch must be clearly marked. It should have permanent wording saying main switch, and it must stand out from other switches so that anyone, even in an emergency, can find it quickly. If there are multiple main switches, each one must indicate which installation or which supply it controls. If operating the main switch also switches an alternative supply, such as a generator, this must be clearly shown. The whole purpose is to avoid confusion and allow fast, confident operation. Clause 2.3.3.5 Remote Control. Sometimes a main switch is operated from a remote location. If so, the remote controls must be clearly marked and located so the operator knows exactly what they are switching. When a remote control system is used, it must be designed so the main switch cannot close by accident because of a fault in the wiring or controls. If closing the main switch is allowed remotely, the device must have a reliable way to keep the switch locked in the open position when needed. The general idea is that remote main switching must be as safe as operating the switch directly. Clause 2.3.4 Additional isolating switches. This clause introduces the idea that, aside from the main switch, some parts of the installation may need extra isolating switches. These additional switches are required when parts of the installation must be isolated independently for safety, for maintenance, or because of the way the building is arranged. The detailed requirements follow in the subclauses. Clause 2.3.4.1 Electrical installation in an outbuilding. This clause explains that an outbuilding can be treated as a separate electrical installation. If the outbuilding has a maximum demand of around 100 amps per phase, or if it has its own switchboard, then it must be treated separately. A main or isolating switch must be installed on the switchboard inside the outbuilding, and it must be able to isolate all supply to that outbuilding. If the outbuilding has more than one submain supplying it, each submain must have its own isolating switch. These switches do not have to be beside each other, but clear permanent notices must show where each switch is located. This prevents a person from thinking they have isolated the building when another supply is still live. Clause 2.3.4.2 Submains and final subcircuits greater than 100 amps. Any submain or final subcircuit with a rating above 100 amps per phase must have its own isolating switch at the switchboard where the circuit originates. This ensures safe control and safe maintenance of high current circuits, which carry more risk if left energized. Clause 2.3.4.3 Alternative supply. When an installation has an alternative supply, such as a generator or inverter, an isolating switch must be provided either at the point where that supply enters the installation or on the relevant switchboard. The isolating switch must be clearly marked to show which circuits the alternative supply covers. If the alternative supply can automatically energize part of the installation, the switch must also indicate clearly what will happen when it operates. This prevents confusion and accidental energizing during maintenance. Clause 2.3.4.4 Identification. All isolating switches in this clause must be clearly and permanently identified so anyone can see exactly what they isolate. If the control for an isolator must be placed away from the switchboard, then a clear warning notice must be installed, describing the operation of the isolator and the circuits it affects. The goal is to prevent a situation where someone misunderstands how the isolation works. Clause 2.3.4.5 Appliances and accessories. Many appliances and accessories require their own isolation or switching. These include water heaters, ovens, motors, room heaters, air conditioners, and safety services. The detailed requirements are found in sections 4 and 7. The main ideas: whenever an appliance might need service or might create danger if accidentally energized, it must have a way to isolate it safely and locally. Clause 2.3.5 Emergency switching including emergency stopping. This clause introduces the idea of emergency switching. Emergency switching is used when we need to quickly remove danger by stopping electricity from flowing. It is not about routine isolation or maintenance, it is specifically for unexpected danger, sudden risk, or unsafe operating conditions. Clause 2.3.5.1 General. This clause tells us that every electrical installation must have a way to perform emergency switching on any part of the installation where electrical power could create an unexpected danger. Emergency switching must be able to stop the supply fast enough to remove the hazard. This can include stopping machines, stopping motors, or cutting power to equipment that could harm a person. Clause 2.3.5.2 Emergency switching devices. This clause explains what equipment can be used for emergency switching. An emergency switch can be a single switching device that interrupts the incoming supply, or a combination of devices that work together so one single action removes power from the dangerous part of the installation. The device must be able to break the full load current of the equipment. It must also be manually operated, clearly marked, and must reliably stay in the off or stop position until reset manually. The device must not re-energize automatically. Power must only return once a person intentionally restores it by operating the switch or control. This prevents machinery from restarting suddenly and injuring someone. Clause 2.3.5.3 Installation. This clause explains how emergency switching devices must be installed. The device must be placed where it is easy to reach and easy to see when danger occurs. Anyone nearby must be able to operate it quickly. Emergency switches must be clearly marked, easy to understand, and located at a position where a person can use them without exposing themselves to extra danger. A socket outlet must not be used as an emergency switch, unless the equipment is supplied only through that socket and the switch on the socket acts as the emergency device. Clause 2.3.5.4 Identification. This clause tells us how emergency devices must be marked. Any switch used for emergency stopping must be clearly marked or colored so that it can be identified straight away. Push buttons or handles should normally be colored red with a contrasting background. The goal is that anyone, even someone not familiar with the equipment, can immediately tell which switch will stop the danger. If a remote lanyard or chain is used, such as above a conveyor, it does not need to be colored red. Clause 2.3.6 Shutting down for mechanical maintenance. This clause introduces the requirement for equipment to be safely shut down when mechanical maintenance work is needed. Mechanical maintenance can involve physical injury risks, such as moving machinery, heat, rotating parts, hydraulic pressure, or unexpected movement. To protect workers, electrical supply must be able to be disconnected safely. Clause 2.3.6.1 General. This clause explains the general rule. A safe means of disconnecting electrical supply must be available whenever mechanical maintenance is carried out on electrically powered equipment. Many machines, like cranes, elevators, conveyors, or pumps, need clear isolation because mechanical hazards may continue even after electrical power is removed. For this reason, the means of shutting down must be secure, reliable, and capable of being locked or secured in the open position if required. Some equipment powered by hydraulic or pneumatic systems may need additional precautions, because removing electrical power alone may not remove the hazard. Clause 2.3.6.2 Devices for shutting down. This clause details the requirements for the devices used for shutting down equipment during mechanical maintenance. The device must be manually operated, clearly show that it is in the off position, be designed to prevent accidental closure caused by impact, vibration, or other disturbance. This ensures the equipment cannot restart unexpectedly while someone is working on it. Clause 2.3.6.3 Installation. Here the standard explains how the shutting down device must be installed. It must be inserted into the main circuit of the equipment, and if it is a switch, it must be capable of interrupting the full load current of that equipment. If the machine uses a control system where stopping the control circuit alone removes the hazard, the standard allows this, but only when suitable safeguards are in place. A remote device may be used for shutting down, provided it can be locked or secured in the open position and prevent accidental operation. Clause 2.3.6.4 Identification. This clause requires all shutting down devices for mechanical maintenance to be clearly marked and easy to identify. Anyone performing maintenance must be able to find the device quickly and confirm that it controls the correct part of the installation. Clause 2.3.7 Functional control switching. This clause deals with switching that is used for normal operation of equipment. This is not about safety, and not about emergency shutdown. Functional switching is simply the switching we use every day to turn equipment on and off during normal use. Clause 2.3.7.1 General. Functional switching is used when we need to control equipment in the normal course of operation. For example, turning lights on or off, controlling motors, controlling appliances, or switching different functions of machinery. A functional switching device must be provided for each part of a circuit or each piece of equipment that needs to be controlled separately from other parts of the installation. One functional switch may control several items at the same time, if they are meant to operate together. Sometimes the switching device is physically part of the equipment itself, for example, a power button on a machine. The key idea is that the device is intended for normal operating control, not for isolation or emergency stopping. Clause 2.3.7.2 Functional switching devices. This clause explains what devices can and cannot be used for functional switching. Functional switching must not be carried out by disconnectors, fuses, or links. Those devices are not designed to handle the regular switching duty that comes with everyday operation. Instead, the switching device must be suitable for the heaviest or most demanding duty that it may need to handle. This includes the type of load, how often the switch will be operated, and the electrical stresses it will face. Functional switches do not need to switch all live conductors, because they are not used for isolation. When functional switching controls equipment with a very low power factor, such as motors or fluorescent lighting, the switch may need a derating factor. This is because low power factor loads place more stress on the switching contacts. However, if a switch is specifically designed for that purpose, the derating may not be needed. The key teaching point is, functional switches must be selected for the operational duty of the load, not for isolation or safety functions. Clause 2.3.7.3 Identification. In this clause, the standard explains that functional switching devices do not need to show on or off positions. This is because their purpose is purely operational, not safety related. However, appliance switches must still show the off position so the user can clearly confirm when the appliance has been switched off. The main idea is that functional switching devices do not need formal identification markings unless other standards require it. Clause 2.3.7.4 Control circuits. This clause deals with control circuits used for switching operations. Control circuits must be designed and arranged so they do not create danger if a fault occurs. For example, a fault in a control wire must not cause machinery to start unexpectedly, stop unpredictably, or operate in a way that could cause harm. Control circuits must also be protected from faults that could cause them to malfunction or cause unintended equipment behavior. A simple way to explain this is: the control circuit must be safe, reliable, and must not allow equipment to behave in a dangerous or uncontrolled way if something goes wrong. Clause 2.4 Fault protection. This whole part of Section 2 explains how we protect people and property when a fault occurs, such as a live conductor touching exposed metalwork, or insulation failing. Fault protection is all about preventing electric shock, fire, or damage when something goes wrong in the electrical system. Clause 2.4.1 General. Here the standard explains the main methods used for fault protection. The first method is automatic disconnection of supply. This means that if a fault occurs, a protective device must disconnect power fast enough to keep touch voltages at a safe level. You'll learn more about that in the later clauses. The second method is using Class 2 equipment or equivalent insulation, which means equipment that does not rely on earthing for safety. The third method is electrical separation, which is used in special situations to limit the risk of shock by isolating a circuit from earth. This clause reminds us that the detailed rules for automatic disconnection are found in clauses 2.4.2, 2.4.3, 2.5, and 2.6. Clause 2.4.2 Protection by automatic disconnection of supply. This clause explains what automatic disconnection is trying to achieve. When a fault occurs between a live part and exposed metalwork, we want the voltage on that metalwork to rise only briefly and then quickly return to a safe level. This is done by ensuring the protective earthing system creates a fault current large enough to operate a protective device, like a circuit breaker or an RCD, which then disconnects the supply. Two things must happen. First, all exposed metal parts must be connected to a suitable earthing system. This allows the fault current to flow safely and ensures the voltage rises high enough to operate the protective device. Second, the protective device, whether an overcurrent device or an RCD, must disconnect the fault fast enough to prevent danger. The basic message is: a good earth connection plus a fast protective device equals safe fault protection. Clause 2.4.3 Types of devices. This clause lists the types of devices that can be used to provide automatic disconnection of supply. But the main idea is simple. The device must be able to disconnect power safely and must not close again automatically. Devices used include fuse links that comply with their correct standard, miniature circuit breakers, molded case circuit breakers, fixed setting RCDs, other protective devices that do not have an automatic reclosing function. Semi-enclosed rewirable fuses are not allowed for this purpose. The key requirement is that the protective device must operate correctly on a fault and must not reconnect itself after clearing that fault. Clause 2.4.4 Auto-reclose devices. This clause deals with devices that can automatically reclose after a fault, such as some circuit breakers used in other parts of the industry. In normal electrical installations, auto-reclose devices are not generally suitable for fault protection unless very specific safety conditions are met. For an auto-reclose device to be allowed, the following conditions must all be satisfied. Condition A. The device cannot be used to meet basic shock protection requirements. Condition B. After someone manually switches the device off, the automatic reclose must not be able to operate. This prevents accidental re-energizing during work. Condition C. A clear warning notice must be present, telling users that the auto-reclose must be disabled before doing any work, and reminding them to follow isolation requirements. Condition D. There must be a time delay before the first automatic reclose, often several minutes, to reduce the risk of an immediate reclosing on a persistent fault. Condition E. The number of reclosing attempts must be limited. Some devices are allowed to skip condition A if they can automatically test the insulation before reclosing. This ensures the circuit is still safe before power returns. The overall lesson here is this. Auto-reclose devices are only permitted when they have built-in safeguards to prevent unexpected energizing that could harm a person working on the system. Clause 2.5. Protection against overcurrent. This part of the standard deals with protecting conductors and equipment when too much current flows. Too much current can be caused by an overload or by a short circuit. If we do not control overcurrent, conductors may overheat, insulation may fail, and equipment may be damaged or catch fire. Clause 2.5.1 General. This clause explains the overall purpose of overcurrent protection. All active conductors must be protected by devices that automatically disconnect the supply whenever current rises above a safe limit. The idea is to disconnect the circuit before the excessive current causes injury or damage. A neutral conductor must never contain a fuse, because disconnecting the neutral alone can create dangerous situations. If a device switches the neutral, it must meet the rules for switching all supply conductors. Protection against overcurrent must cover two conditions. First, protection against overload current, when a circuit carries more current than it is designed for over a period of time. Second, protection against short-circuit current, when a fault causes extremely high current to flow suddenly. These two forms of protection must work together and must coordinate correctly so that the right device operates at the right time. Clause 2.5.1.1 Consumers' Mains. This clause explains how overcurrent protection applies to consumers' mains, the conductors supplying the building from the point of supply. There are several ways the overcurrent protection for consumers' mains may be arranged. Option A is to provide both short-circuit protection and overload protection at the origin of the consumer's mains. Option B is to provide short-circuit protection at the origin of the mains, and provide overload protection later at the main switchboard. Option C allows cases where overload protection at the main switchboard is considered enough, when the mains are installed in a way that limits the risk of overtemperature. In this case, short-circuit protection may be supplied by equipment at the switchboard or by a service protective device. The key teaching point is that consumers' mains must always have effective short-circuit protection, and overload protection must be provided either at the origin or at the main switchboard, depending on the installation method. Consumers' mains that feed circuits already individually protected against overload are considered to have overload protection, as long as the combined ratings of those downstream devices do not exceed the current carrying capacity of the mains. Clause 2.5.1.2 Submains and final subcircuits. This clause explains that every submain and final subcircuit must have overcurrent protection at the point where the conductor size reduces or at the point where the circuit begins. The protective device must protect the conductor against both overload current and short-circuit current. There are a few exceptions. Overcurrent protection must not be installed where opening the circuit could create a greater hazard, for example, in some safety-critical circuits. Overcurrent protection may be placed at another location, as allowed in later clauses. In some situations, the device may be omitted if other parts of the installation already provide equivalent protection. In simple terms, every cable must be protected where it starts or where it becomes smaller, unless a special rule says otherwise. Clause 2.5.1.3 Omission of protective device for safety reasons. This clause explains when a protective device may not be installed. If opening a circuit unexpectedly could create a dangerous situation, then overcurrent protection may be intentionally omitted. This applies to certain safety systems, lifting magnets, emergency supplies, or control circuits that must never lose power suddenly. In these cases, other safeguards, such as alarms or supervision, may be required to manage risks without relying on overcurrent protection. The main idea is, if disconnecting the circuit is more dangerous than leaving it energized, then we do not use a protective device that can open automatically. Clause 2.5.2 Devices for protection against both overload and short-circuit currents. This clause describes devices that can provide full overcurrent protection. A protective device must be able to break any overload or short-circuit current that might occur at its location. This includes very high prospective fault currents. If a device cannot break the full fault current, it may still be used, but only if another device is installed in series to provide the required breaking capacity. This is sometimes called backup protection. The device must comply with the requirements of the later clauses 2.5.3 and 2.5.4. Suitable protective devices include circuit breakers with both overload and short-circuit protection, fuse switch combinations, high rupturing capacity fuses, circuit breakers used together with fuses. Semi-enclosed rewirable fuses cannot be used for full fault protection. The key learning point here is the protective device must safely interrupt the worst-case fault current that could appear at that point in the installation. Clause 2.5.3 Protection against overload current. This clause explains how we protect conductors and equipment from overload, which means current that is too high for too long, but not necessarily caused by a fault. Overload currents can overheat cables and damage insulation if they are not controlled. Clause 2.5.3.1 Coordination between conductors and protective devices. This clause tells us that the protective device and the conductor must be matched correctly. A conductor has a certain current carrying capacity, called IZ. The protective device has a rated current, IN, and the circuit is designed for a certain current IB. To prevent damage, IB must be less than or equal to IN, and IN must be less than or equal to IZ. This simply means design current less than or equal to fuse or breaker rating less than or equal to cable capacity. The device must also operate in time to protect the cable when an overload happens. Circuit breakers and fuses have different operating curves, but the goal is the same: prevent cable overheating. For fuses, the rating is usually reduced to ensure the cable is still protected. For example, a fuse is often chosen at not more than 90% of the cable's capacity. The big idea is the cable must always be able to safely carry whatever current the protective device allows. Clause 2.5.3.2 Position of overload protective device. This clause says the overload protective device must normally be installed at the point where the circuit begins, or where the cable size reduces. This prevents a long length of cable from being unprotected. There are exceptions covered in later clauses, but the general rule is simple. Protect the cable at the start of the run. Clause 2.5.3.3 Alternative position of overload protective device. This clause explains when the overload device may be installed somewhere other than the start of the cable. This is allowed when the cable does not supply branch circuits or socket outlets before reaching the protective device, or the cable only supplies circuits that already have overload protection, and the total downstream ratings do not exceed the cable's capacity. This arrangement is common in side switchboards or bizways, where the layout makes it safe to place the protective device further along the cable. The key idea: you can move the overload protection, but only if the cable is not placed at risk in the unprotected section. Clause 2.5.3.4 Emission of overload protective device. In some situations, overload protection may be intentionally left out. This is only allowed when first, opening the circuit unexpectedly could create a more dangerous situation than the overload itself. This applies to some safety systems and specialized industrial equipment. Second, the conductor must not be in a location where fire risk or explosion risk is high. Third, the equipment supplied must not be capable of causing overload, for example, some heating appliances or transformers with known characteristics. Fourth, the conductor must not supply branch circuits or socket outlets before reaching a device that does provide protection. The big message here is overload protection can be omitted only when the installation design makes overloads impossible or when disconnection would be unsafe. Clause 2.5.4, Protection against short-circuit current. This clause deals with very high fault currents caused by short circuits. Short circuits can reach thousands of amps and must be cleared extremely quickly to prevent fire or severe damage. Short circuit protection must take into account all possible fault paths between conductors of the same circuit. Clause 2.5.4.1, Determination of prospective short-circuit current. Before choosing protective devices, the installer must know the highest short-circuit current that may occur at each point in the installation. This can be calculated or measured. Knowing this value ensures that circuit breakers or fuses are rated to interrupt the maximum possible fault current safely. A device with too low a breaking capacity can explode or fail dangerously. Clause 2.5.4.2, Position of devices for short-circuit protection. Short-circuit protection must usually be placed at the point where the circuit begins or where the cable size reduces, similar to overload protection. This ensures no section of cable is exposed to the risk of a high fault current without protection. There are exceptions, covered in the next subclauses. Clause 2.5.4.3, Alternative position of short-circuit protective device. This clause explains when short-circuit protection can be moved from the normal position. Clause 2.5.4.3.1, Condition 1. A protective device may be installed later in the circuit if the unprotected cable is not longer than about 3 meters. The cable is installed so that mechanical damage is unlikely, and it is located where fire or shock risk is very low. This is often used inside switchboards or between closely located enclosures. Clause 2.5.4.3.2, Condition 2. The protective device may also be installed on the supply side of a reduction in cable size if the device still protects the smaller conductor, and the let-through energy of the device is low enough that the smaller cable will not be damaged. This requires coordinating the characteristics of the protective device with the cable. The big idea. Short, safe cable sections may be left temporarily unprotected, but only under tightly controlled conditions. Clause 2.5.4.4, Omission of devices for short-circuit protection. This clause lists cases where short-circuit protection may be omitted. These include circuits where disconnection would be dangerous, certain consumers' mains installed in specific ways, cables connecting generators, transformers, or batteries to switchboards, provided the wiring is arranged to minimize short-circuit risk and the protective device is located at the associated switchboard. In summary, short-circuit protection may be omitted only when the wiring method itself keeps the risk extremely low. Clause 2.5.4.5, Characteristics of short-circuit protective devices. This final clause describes what a short-circuit protective device must be able to do. The device must have a breaking capacity that is equal to or greater than the fault current at the point where it is installed. If a device with a lower rating is used, it must be backed up by another device on the supply side that limits the energy to a safe level. The protective device must also operate fast enough to keep the cable temperature below its maximum safe limit. This prevents insulation damage. In simple terms, short-circuit devices must interrupt the fault safely and quickly without letting the cable overheat. Clause 2.5.5, Protection against switchboard internal arcing fault currents. This clause deals with arcing faults that happen inside a switchboard. An arcing fault is when electricity jumps through the air between conductors or metalwork, creating extremely high heat and pressure. These faults are dangerous, and heavy current switchboards must be designed to reduce the chance of an arc starting, and to reduce the damage if one does occur. A heavy current switchboard means the supply to the switchboard is 800 amps or more per phase. The rule is that the supply conductors, right up to the line side of the protective device, must be arranged so that the chance of an arcing fault is reduced, usually by insulation or by separation. Then the switchboard itself must comply with one of the following. First option, Clause 2.5.5.2, reduce the chance of the arc starting. Second option, Clause 2.5.5.3, if an arc does start, limit the harmful effects as much as possible. Third option, use both ideas together, provide internal separation as required in Clause 2.5.5.2, and also limit the harmful effects under Clause 2.5.5.3. Clause 2.5.5.1 General. This clause explains the overall intention. During normal operation or during maintenance, the switchboard must have features that reduce the chance of an arcing fault starting. It also reminds us that internal separation is not always about preventing contact with live bare bus bars. For example, an enclosure rated IP2X can still use bare bus bars inside because the protection prevents people from touching them. Clause 2.5.5.2 Reduction of the probability of the initiation of a switchboard internal arcing fault. This clause explains how separation inside the switchboard reduces the chance of an arc starting. Heavy current switchboards must have internal separation to at least the level described in the switchboard standards. This separation applies between bus bars and functional units, functional units from each other, terminals for external conductors, and in some cases, a safety service section. The general idea is that by physically separating parts, a fault in one part is less likely to spread or initiate an arc elsewhere. Clause 2.5.5.3 Limitation of the harmful effects of a switchboard internal arcing fault. If an arc does start, protective devices must try to minimize the damage. The standard assumes that internal arcing fault current will usually be between 30% and 60% of the prospective short-circuit current. This is lower because the arc voltage reduces the current. Protection must operate quickly. It must pick up at a current less than 30% of the three-phase prospective current. There is also a calculation to find the maximum clearing time that still keeps damage acceptable. The calculation uses a constant K sub E, the current rating of the switchboard, and 30% of the prospective fault current. The aim is to clear the arc quickly enough so the switchboard is not destroyed. The example shows how an 800 amp switchboard with a fault of 16.67 kA leads to a required clearing time of less than 0.57 seconds. The settings of protective devices must be as low as possible while still allowing equipment like motors to start. And earth fault devices must not be set above 1200 amps. Where arc detection equipment is used, it must ignore stray light sources but must still detect real arcs. Arc detectors do not remove the need for discrimination between protective devices. Clause 2.5.6 Coordination of overload and short-circuit protective devices. This clause explains how overload protection and short-circuit protection must work together so that conductors and equipment are fully protected. There are two ways this coordination can be achieved. Either by one protective device, or by separate devices that work together. Clause 2.5.6.1 Protection afforded by one device. Here the standard explains that one device can provide both overload and short-circuit protection as long as it meets the overload protection rules in Clause 2.5.3 and it has a braking capacity at least equal to the prospective short-circuit current at its installation point. If both of these conditions are met, the device is considered to protect the whole load side conductor from both overload and short circuit. There is a note that says this may not always be true for extremely high short circuit currents or for certain circuit breaker types, especially non-current limiting types. If there is any doubt, the characteristics of the device must be checked using Clause 2.5.4.2. Clause 2.5.6.2 Protection afforded by separate devices. Sometimes overload protection and short-circuit protection are provided by different devices. In this case, the overload device must meet Clause 2.5.3. The short-circuit device must meet Clause 2.5.4. And both devices must be coordinated so that the energy allowed through during a short circuit does not exceed what the conductor or equipment on the load side can withstand. This prevents the conductor from overheating or being damaged before the short-circuit device disconnects. The coordination is normally confirmed by checking manufacturer data or by inspection under Clause 8.2.2. Clause 2.5.7, Reliability of supply. Clause 2.5.7 is all about keeping the power on as much as possible when something goes wrong. The idea is simple. When we design an electrical installation, we don't want one fault to shut down the whole place. So the installation should be divided into sensible circuits, and each circuit should have protective devices chosen and set so they work together properly. This means if a fault happens on one circuit, only that affected circuit loses supply. Everything else keeps running normally. The protective devices should be selected so they do not trip too easily, and should also be adjusted to work in the right order. The standard also reminds us that the settings of these devices must be checked during inspection. That makes sure the discrimination is correct and the supply stays reliable. Clause 2.5.7.1, General. Clause 2.5.7.1 repeats the key idea in a simple way. The installation must be arranged so supply is reliable. That reliability is achieved by dividing the wiring into suitable circuits and choosing protective devices that will operate in the right sequence. The goal is that when a protective device trips, it affects the smallest area possible. Only the faulty part goes off, and all the other parts continue supplying power. Again, the settings must be inspected to ensure the protective devices are coordinated properly. Clause 2.5.7.2, Coordination of protective devices. Clause 2.5.7.2 introduces the idea of coordinating different protective devices. When we have more than one protective device on a circuit path, they must work in the correct order. This is often called discrimination or cascading. We want the device closest to the fault to trip first. The upstream devices, the ones further back toward the supply, should not operate unless absolutely necessary. That prevents large parts of the installation from losing power due to a small fault. The overall aim is to make sure protective devices understand their job, so the right device trips at the right time, and supply to the rest of the system is maintained. Clause 2.5.7.2.1, General. Clause 2.5.7.2.1 explains the general idea of discrimination between protective devices. It tells us that discrimination is achieved when a downstream device clears the fault while the upstream device stays closed. In other words, the protective device nearest the fault trips, and everything upstream carries on supplying power normally. The clause also highlights that discrimination depends on the time and current curves of the devices. The downstream device must operate faster or at a lower current than the upstream device. That way, only the faulty section is disconnected. Clause 2.5.7.2.2, Safety Service Circuit Discrimination. Clause 2.5.7.2.2 focuses on safety services. These are installations that must keep working during an emergency, such as alarms, evacuation systems, and some lighting. For these circuits, discrimination must ensure that a fault on a normal circuit will not interrupt the safety service. Likewise, a fault on the safety service circuit must not cause loss of supply to other safety circuits. The design must protect the function of these essential systems, even during faults. Clause 2.5.7.3, General Supply Circuit Discrimination. Clause 2.5.7.3 deals with normal electrical circuits. Just like the earlier clauses, the goal is to minimize loss of supply. Protective devices must be arranged so that downstream devices trip before upstream devices. The clause goes on to explain the different ways this discrimination can be achieved, especially when using circuit breakers or fuses. The operating curves must be chosen so they do not overlap in a way that causes the wrong device to trip first. The designer must ensure the protective devices are selected and adjusted so that overload and short-circuit discrimination is maintained as much as possible. Clause 2.6, Additional protection by residual current devices. Clause 2.6 introduces the idea of extra protection using RCDs. This section explains when RCDs are needed, what type should be used, and how they should be arranged in an installation to give better protection against electric shock and fire risk. Clause 2.6.1, General. Clause 2.6.1 explains that a fixed setting RCD with a rated residual current not greater than 30 mA is recognized as providing additional protection. This is especially useful in situations where a basic fault, or careless use of equipment, could expose someone to dangerous shock. This extra protection does not replace the main protective measures in Clause 2.4. It simply adds another layer of safety. An important point in this clause is that RCDs do not protect against faults between active conductors, and they do not protect against voltages imported through the neutral of the supply system. They are designed mainly to protect people from leakage to earth. This clause also tells us that when Clause 2.6.3 requires it, the RCD must disconnect automatically when the leakage current reaches the trip value. Clause 2.6.2 Selection and arrangement of devices. This clause explains how to choose the right type of RCD and how to arrange them in an installation. Clause 2.6.2.1 General. Clause 2.6.2.1 sets out the basic requirements for choosing the RCD. Any RCD used for additional protection must be able to interrupt the supply when the earth leakage current exceeds the designed limit. The RCD must have a load current rating high enough for the part of the installation it protects. This means the RCD must handle the maximum load expected on that circuit, and the rating cannot be less than the rating of the overload device on the circuit. The earth or bonding conductor must not pass through the RCD's magnetic core, because that would stop the RCD from sensing the leakage current properly. RCDs must also be arranged in a way that avoids nuisance tripping. This means the normal leakage from equipment on that circuit should not be too close to the RCD's trip level. Clause 2.6.2.2 Types of RCD. Clause 2.6.2.2 explains the different RCD types used in New Zealand, and what types of leakage each device can sense. In simple spoken form, Type A RCDs respond to AC leakage and pulsating DC leakage. Type F RCDs respond to more complex leakage, including leakage from equipment with electronic speed control or frequency converters. Type B RCDs respond to almost all forms of leakage, including smooth DC and higher frequency components. These are used for specialized loads. This clause also mentions that the shape of the leakage current, the waveform, affects how the RCD operates. Selecting the correct type ensures reliable protection. Clause 2.6.2.3 Protection against initiation of fire. Clause 2.6.2.3 explains that RCDs can also help reduce the chance of electrical fires caused by insulation failure. This is not a compulsory part of the standard, but a Type S RCD with a higher rated residual current, typically 100 to 300 mA, may be used where extra fire protection is wanted. This is in addition to the requirements of Clause 2.6.3. These devices do not provide personal shock protection. Their purpose is to limit overheating of insulation and reduce fire risk. Clause 2.6.2.4 Arrangement. Clause 2.6.2.4 explains how final subcircuits must be arranged when additional RCD protection is required. The rules are simple. In any installation with more than one RCD and more than one lighting circuit, the lighting circuits must be shared between the RCDs. This avoids the whole building becoming dark if one RCD trips. In a residential installation, not more than 3 final subcircuits should be connected to a single RCD. If the home has more than one final subcircuit, then at least 2 RCDs must be installed. The aim is to reduce inconvenience and improve safety by avoiding a single point of failure. Clause 2.6.3, where additional protection is required. Clause 2.6.3 explains when RCDs must be used to give additional protection on final subcircuits. The goal is to reduce shock risk in places where people commonly plug in equipment, touch appliances, or where children may be present. Clause 2.6.3.1 Residential electric installations. Clause 2.6.3.1 tells us that a 30 mA RCD must protect certain final subcircuits in residential type areas. These include subcircuits supplying one or more socket outlets, Subcircuits supplying lighting points. Subcircuits supplying directly connected handheld equipment, such as hairdryers or portable tools. These requirements apply to individual domestic homes, the residential areas of other buildings, groups of residential units that share common areas, external lighting in shared spaces around residential buildings. This clause also states that the RCD must be installed at the switchboard where that final subcircuit begins. There are some exceptions. For example, medical treatment areas used for home dialysis follow the special rules in ASNZS 3003. Some alterations or repairs may not require RCD protection if they meet the conditions in Clause 2.6.3.4. A socket outlet for a fixed cooking appliance may not need an RCD if it is in a location not normally accessed by the general public and is clearly marked for its restricted purpose. This clause aims to make sure that places where people live and move around most often have strong shock protection. Clause 2.6.3.2 Other electrical installations. This clause covers non-residential installations. It has different rules depending on the type of space. Clause 2.6.3.2.2, New Zealand. Clause 2.6.3.2.2 explains that in New Zealand, certain areas used for children must have extra protection using a 10 mA RCD. These areas include kindergartens, daycare centres for preschool children, schools for children up to around year 8. There are exceptions. For example, socket outlets mounted higher than 1.8 meters. Outlets used only for clearly marked equipment such as IT gear or cleaning equipment. Outlets in corridors, halls, gymnasiums or similar places where children are unlikely to use portable appliances. Places where other methods of protection exist, such as separated supply. Places where other standards require different RCD arrangements. Special locations in Sections 6 and 7, where different protection rules apply. This clause aims to protect younger children, who face a higher risk of electric shock. Clause 2.6.3.3, Home medical patient treatment installations. Clause 2.6.3.3 applies to homes where medical electrical equipment is used under the rules of ASNZS 3003. These installations must be supplied by a dedicated circuit, be protected by a Type A RCD rated at 10 mA, allow the patient or carer to reset the RCD if needed. The idea is to provide both safety and practicality in home healthcare environments. Clause 2.6.3.4, Alterations, additions and repairs. Clause 2.6.3.4 explains that when a switchboard's circuit protection is replaced, the new arrangement must include RCD protection for all the final subcircuits supplied from that switchboard, if required by Clause 2.6. Any new socket outlet added to an existing circuit must be protected by an RCD. There are exceptions. If a socket outlet or lighting point being replaced was not originally RCD protected, you do not need to add RCD protection just for a straight replacement. If lighting-only subcircuits are being extended, RCD protection is not required if the existing lighting subcircuit was not RCD protected. If socket outlets are added in a situation where an exception from Clause 2.6.3.1 or 2.6.3.2 applies, then RCD protection may not be required. The purpose of this clause is to make sure upgrades bring improved safety, while avoiding unnecessary work when the risk is low. Clause 2.7, Protection against overvoltage. Clause 2.7 introduces the requirements for protecting an electrical installation from dangerous overvoltage conditions. Overvoltage can damage equipment or create hazards for people and animals. Clause 2.7.1 General. Clause 2.7.1 explains that if overvoltage could cause danger, then the installation must be protected in line with clauses 2.7.2 and 2.7.3. It also highlights common causes of overvoltage, such as faults between circuits of different voltage levels, switching operations, lightning, Resonance effects. Protection against overvoltage is especially important in regions with frequent lightning activity. Clause 2.7.2, Protection by insulation or separation. Clause 2.7.2 covers how insulation or physical separation can prevent dangerous overvoltage effects between parts of the installation. This includes using adequate insulation or screening for conductors, providing insulation or screening between transformer windings operating at different voltages, ensuring that if a transformer fault occurs, the protective earthing system causes the supply to disconnect. The key idea is that physical barriers or insulating materials help stop high-voltage faults from affecting low-voltage circuits. Clause 2.7.3, Protection by protective devices. Clause 2.7.3 describes how protective devices, such as surge protection devices, can be used to handle overvoltage from lightning or switching operations. Where these devices are installed, they must limit the overvoltage to a safe level below the insulation rating of the equipment, operate at voltages appropriate for normal conditions, not cause hazards to people or animals during operation. This clause also explains that the standard does not force every installation to have surge protection. Instead, Appendix F gives guidance on when surge protection may be appropriate and how it should be selected. Clause 2.8, Protection against undervoltage. Clause 2.8.1, General. This clause explains that we need protection when the supply voltage drops too low, or when the voltage disappears and then suddenly returns. Either situation can create danger to people or property. A sudden return of voltage can cause machinery to restart without warning. A low voltage can make motors struggle, stall, overheat, or fail to start at all. So if these risks are present, undervoltage protection must be installed. There is one exception. If the only risk is damage to equipment, and the owner accepts that risk, then undervoltage protection may be left out. Clause 2.8.2, Selection of protective device. The undervoltage protective device must be suitable for the type of equipment it is protecting. It must follow the rules and the relevant standards, especially for motor starting. If automatic reclosing of the device could be dangerous, it must not reclose automatically. In other words, when the voltage comes back, the equipment should not restart if that restart could harm someone. The device must disconnect quickly when the voltage drops. But if the equipment can safely tolerate a very short dip, then a brief delay is allowed. Examples of undervoltage devices include relays operating a switch or breaker, and non-latched contactors that release when voltage falls. Clause 2.9, Switchboards. Clause 2.9.1, General. Every electrical installation must have one or more switchboards. This is where the main switch and protective devices are located and controlled. There is an exception for some underground distribution systems that use special cable cabinets instead of a normal switchboard. A main switchboard must be provided for each electrical installation. This board holds the main switch, protective devices, and control equipment. Clause 2.9.2, Location of switchboards. Clause 2.9.2.1, General. Switchboards must be installed in well-ventilated places. They must be protected from moisture. They must also have enough space around them so electricians can install, test, maintain, and repair equipment safely. Clause 2.9.2.2, Accessibility and emergency exit facilities. Switchboards must be placed so that access is not blocked by walls, fittings, or furniture. There must be enough space around all sides where work may be done. People must be able to leave the switchboard area quickly in an emergency. This includes a clear working space of at least 0.6 meters in front of the switchboard, an alternative exit path if the switchboard is longer than 3 meters, or if the fault current is high, or if the installation needs 2 escape routes. Doorways must be at least 0.75 meters wide and 1.98 meters high to allow safe entry and exit. Switchroom doors must open in the direction of escape and must be able to open without a key or tool. Where a switchboard has 2 doors, Those doors should be spaced well apart. If a switchboard is in a narrow space, the door must be able to be fixed in the open position so that workers are not pushed toward live parts. There is one exception. These special door and emergency exit rules do not apply to small domestic electrical installations. Clause 2.9.2.3, Location of main switchboard. The main switchboard needs to be easy for people to reach. It must be placed where someone can quickly get to it from an entrance to the building. This is because the main switchboard is the central point for controlling the installation. In places with more than one electrical installation inside the same building, the main switchboard cannot be hidden inside one tenancy or one private area. It has to be in a shared location so that it is available for everyone who needs access, including emergency services. Clause 2.9.92.4, Identification of main switchboard. The main switchboard must have a clear and permanent label that says main switchboard. If the switchboard is inside a room or an enclosure, then any door that someone must open to reach the switchboard also needs a clear label showing that the switchboard is inside. The position of the main switchboard must be identified by a sign at each entry to the building that emergency workers might use. These signs must be permanent and must stand out. The words main switchboard need to be shown in contrasting colors so they can be seen easily. There are situations where these markings are not required. If it is a single domestic home, the switchboard does not need this level of identification. If the location of the switchboard is already clearly shown on a fire indicator panel at the entrance, another sign is not needed. If the switchboard can be seen immediately when you enter the building, no extra marking is required. In New Zealand, any sign showing the location of the main switchboard must meet the New Zealand Building Code. Clause 2.9.2.5, Restricted locations. There are some places where you are not allowed to install switchboards because it is unsafe or impractical. A switchboard must not be installed higher than 1.2 meters above the ground, the floor, or a platform. This is to make sure it can be reached safely. There is an exception if access to the live parts has been arranged safely under Clause 2.9.3.1. A switchboard must not be installed near water containers or near fixed or stationary cooking appliances. Water, steam, or heat would affect the switchboard. An exception is allowed when the switchboard is enclosed with tight-fitting doors or placed in an enclosure that protects it from splashing or steam. If a switchboard is placed inside a cupboard or enclosure, the cupboard must be designed properly. The switchboard must be in its own section of the cupboard. It must be positioned at the front so a person can operate or maintain it without reaching awkwardly. The cupboard door must not push objects into the switchboard when closed. There must also be no objects in front of the switchboard that make access difficult. A switchboard must not be placed near baths or showers because of moisture and condensation risks. The same rule applies near saunas, swimming pools, or spa areas, as explained in Clause 6.3. A switchboard must not be installed inside a refrigeration room. Switchboards inside areas used for sanitizing or hosing down must have an enclosure with at least IP6X protection. Switchboards must not be installed where people need to pass during an emergency exit. Smoke from a fault inside the switchboard could block escape routes. Switchboards must not be installed in cupboard spaces that contain fire hose reels. They must also not be installed directly under automatic fire sprinkler heads unless certain protective features are provided, such as IP4X protection or splash shields. Switchboards cannot be installed in hazardous areas unless they are specifically designed for those environments in accordance with ASNZS 6007 9.10.1 or ASNZS 6007 9.10.2. Hazardous areas may include places with heavy bottled gas cylinders, gas tank filling points, or pressure relief discharge points for gas installations. New Zealand examples include LPG cylinder areas and natural gas system regulators. Clause 2.9.3 Construction. Clause 2.9.3.1 Access to live parts. This clause explains how a switchboard must be built so people are kept safe from live parts. Live parts must be enclosed so that basic protection is always there. The enclosure is the main safety barrier that keeps people from touching anything energized. There is one situation where live parts may be exposed, but only non-domestic electrical installations. In that case, the live parts must still be arranged so that barriers give basic protection, or the area must only be accessible to authorized people, with proper lockable access. Anytime a cover is removed and live parts become exposed, the switchboard must have clear identification so people know the risks, following the rules in ASNZS 3439. Domestic switchboards do not use this exception. In homes, we never expose live parts. Clause 2.9.3.2 Suitability. Switchboards must be strong enough to handle the real-world stresses they face. They need to withstand mechanical stress, electrical stress, and thermal stress that may happen during normal service or during faults. If a switchboard is built to the ASNZS 3439 series, it is considered suitable. That standard sets the performance expected. There are also extra design requirements for segregation of safety services and for protection against arcing faults, which appear in other parts of ASNZS 3000. Clause 2.9.3.3 Minimum clearances and creepage distances. Bare live conductors must never be too close to other conductors or to earth. A minimum air clearance and a minimum creepage distance must always be maintained. These distances help prevent flashover. Sometimes smaller distances are allowed, but only when the equipment already complies with its own standard, or when a neutral bar or link is insulated from earth. Clause 2.9.3.4 Orientation of circuit breakers. When two or more circuit breakers are mounted in a row, they should all open in the same general direction. This makes it obvious how the device operates and reduces confusion. If the design of a breaker makes the open position very clear, different orientations may be accepted. Clause 2.9.3.5 Screw-in fuses. Where screw-in fuses are used, the connection point must be arranged so the live supply connects to the center contact of the fuse base. This reduces the risk of accidental contact with live threads when changing a fuse. Clause 2.9.4 Bars or links. Clause 2.9.4.1 General. Bars or links must be able to securely terminate conductors. Their design must follow the rules of Clause 3.7 to ensure reliable electrical connections. Clause 2.9.4.2 Tunnel-type terminals. Tunnel-type terminals use screws that clamp the conductor. Any screw that touches a conductor must be designed so it does not cut into the conductor strands. These terminals are often used for important conductors such as the incoming neutral, the main earthing conductor, the MEN link, or APEN conductor. Because these are critical conductors, the terminal must either use two screws or use one screw with a large enough diameter so the conductor is not damaged. Clause 2.9.4.3 Neutral bar or link. Every switchboard must have a proper neutral bar. It must have adequate current carrying capacity and be easy to access so conductors can be connected safely. The bar must also be designed so the incoming neutral cannot be accidentally disconnected. This is important because the incoming neutral stabilizes the whole installation. There must also be separate terminals for the main neutral conductor and the neutral conductors of each outgoing circuit. Where tunnel-type terminals are used for neutrals, the earlier rules for tunnel terminals apply. In some cases, a single neutral bar may be shared across multiple devices on the board, but it must still follow the rules for safe termination and identification. Clause 2.9.4.4 Marking of bars and links. Bars and links must be clearly marked as active, neutral, or earth. This helps anyone working on the switchboard quickly identify the correct connection point. When the insulation color of the connected conductors already makes the function obvious, extra marking may not be required. Clause 2.9.4.5 Terminals of switchboard equipment. All terminals on the switchboard, such as for breakers, fuses, RCDs, and similar devices, must be marked so you can tell which active and which neutral belong together. The MEN connection and the main neutral conductor must also be clearly and permanently marked on the neutral bar, except where the MEN link is at the far end or the neutral bars are directly adjacent and obvious. Where the MEN is at a different location, such as a substation, the main switchboard must still be marked so anyone can identify the correct neutral point. Clause 2.9.4.6 Fuses. If the marking on a fuse holder does not match the actual fuse rating, the correct rating must be clearly marked at the fuse location. This could be on the fuse base, the enclosure, or the switchboard panel. When several identical fuses are used as a group, the rating only needs to be displayed once as long as they are side by side and all have the same rating. Clause 2.9.5 Equipment Identification. Clause 2.9.5.1 General. Everything inside a switchboard must be clearly and permanently identified in English. This includes all equipment, switches, breakers, fuses, RCDs, and other devices. Clause 2.9.5.2 Relationship of electrical equipment. The labeling must show which device controls which part of the installation. Each circuit and each protective device must be marked so there is no confusion. Clause 2.9.5.3 Bars and links. Bars and links must be marked so anyone can tell whether they belong to active, neutral, or earth. If the conductor insulation already makes this obvious, extra marking may not be needed. Clause 2.9.5.4 Terminals of switchboard equipment. Terminals must be marked clearly so each active conductor and its matching neutral conductor can be identified. This prevents wiring mistakes and helps with maintenance. The MEN termination and the main neutral conductor must be marked unless the layout makes it unmistakable. Clause 2.9.5.5 Common neutral. When more than one circuit shares a neutral, that neutral must be permanently marked so the associated active conductors are easy to identify. Clause 2.9.5.6 Fuse. If a fuse base does not clearly show the correct fuse rating, the correct rating must be added as permanent marking. This is important when fuses are grouped or when the original marking is unclear. Clause 2.9.6 Wiring. Wiring inside a switchboard must be installed so it can handle heat, magnetic effects, and movement from hinged panels. Conductors must be long enough so a panel can swing open or be removed without straining the terminals. Wiring must be fixed securely so it does not pull on equipment when the panel moves and so it does not press against devices behind the panel. Clause 2.9.7 Fire protective measures. Wiring around switchboards must be arranged so that if a fire starts in the switchboard, it does not spread easily. Where wiring enters a switchboard enclosure, the entry points must fit closely around the wiring so flames or smoke cannot easily pass through. In many cases, this means using close-fitting openings or fire-resistant sealants. Large openings may need sealing to stop the spread of fire. Internal conduits or wiring ducts inside the switchboard also need sealing if they could allow fire or hot gases to move inside the board. Now that brings us to the end of Section 2 of ASNZS 3000. We have walked through a very big part of the standard, from the basic ideas of protection, through switching, fault protection, overcurrent protection, RCD requirements, overvoltage, undervoltage, and finally the full set of rules for switchboards. It is a long section, but every part of it links back to one simple purpose, and that is to keep people safe and to keep installations working the way they should. If you have followed the whole section with me, you should now have a clearer picture of why each protective measure exists, what the devices are expected to do, and how an installation is arranged so that faults are managed safely. These ideas are the foundation for almost everything you will do as an electrician in New Zealand, whether you are designing, installing, testing, or fault finding. As you move on to the next sections of the standard, keep these principles in mind. Section 2 is really the heart of electrical protection, and the rest of the book builds on the thinking you have learned here. Thanks for staying with me through this whole section. When you're ready, we will continue our journey into the next section of ASNZS 3000.